I'll do an introduction. So that's me at the top here. We're going to go put my name in Google and see what happens. Oh, no, we did that already. So I'll just take the top hit. Always take the top hit. So we'll see what happens here. Oh, there I am. Okay. So that's my web page. And I've got at the very top of it, you see the PASI course. So you want to go there and get information. And if I can do that without... so in particular, you'll see two things there. The lecture notes for today and for the next few days. I'll keep updating that spot. And then what I'm talking about is largely based on a book called Scientific Parallel Computing. And chapter 1 is available from the publisher. So I put it there for you to get and read. And so the idea is that I'd like you to read that as part of the course. And when you download the lecture notes, you should get something that looks like this. And why don't we take a look at that and get going then. Okay. Oh, thank you very much. Okay, good. Thank you. So let me get this blown up to size. Is that it? Okay. And you should be good. Okay. So let me start talking about the landscape. So there's a website that probably most of you know, the top 500 supercomputers, that's tracked the growth of supercomputing for about 20 years. And you can do all kinds of stuff. It's really a database that they keep, and you can draw all kinds of figures. And so I drew the following figure. What I'm showing here is the number of processors, which admittedly is a crude way of measuring things. Now, to be technical, you say the number of cores, but that's the number of processors. And so the axis here is the number of processor cores, and here it's the number of machines with that number of cores. So it's the distribution of machines as a function of the size of the machines. And in blue, we have 2005, and in red, we have June 2010. So what do we see here? Well, we see that the distribution is moving to the right. And you could play this game some more. You could go back in history, and you'd find that the distribution is, marching off this way. And now look at the scale. Well, the scale here is 1 million. So on this scale, we'll be seeing 1 million core processors soon, if not now. And where is the peak? Well, the peak is around 10,000 cores. So that's the landscape today. That's the sort of, when we talk about high-performance computing today, whatever massive parallelism means, 10,000 is the sort of number that we should be shooting for. Okay, so here's just a summary of that information. All of the top 500 machines had more than 1,000 processors. Now, you don't always get all processors, so maybe you say, well, maybe I don't need to be shooting for 1,000 processor efficiency here, but the size is just getting bigger. The majority of the supercomputers today have between 4,000 and 8,000 processors. So that's the scale we should be thinking about of today, and as that distribution is moving to the right, I project that in the next 5 years, this will have scaled up correspondingly. And today there are 5 supercomputers with more than 100,000 processors. So this is big. This is very big. Now, what's the state of the art? Well, in scientific computing, a lot of things have been done. So I think the state of the art is pretty good. And I picked a number of problems which are scalable and I would say pretty well under control. But the last day, on Thursday, I'm going to talk about something completely new where I think there's a real challenge and parallelizing in time for time-dependent problems. And so I hope you'll stick around for that. But here I've taken something that we played with for some time, a multi-grid problem, and computing on 1,000 processors. And this is solving a pretty standard Laplace problem on on a regular grid, but the solution time is only 4 seconds. So this is a problem that has a billion unknowns, and you can solve it in 4 seconds with 1,000 processors. And we'll talk about metrics for understanding this data better. I'm not presenting this as the world's largest computation by far, but I'm just saying that's typical today. So 1,000 processor computation is pretty much bread and butter at this point. Okay, but first I want to talk about applications, because applications are the most important thing. And what is the most important application in science? I should ask one of the distinguished speakers this. Of course, it's employment. The most important application of science is to get a job and make money doing what you like to do. So amazingly enough, on the day after Christmas, this email arrived in my mailbox from someone at Utah saying, we want to hire somebody. The postdoc will be expected to perform algorithmic and parallel computing research to help their system scale to 100,000 cores. Okay, so I reckon that that's my job here today, is to teach you what you need to know to get up to that scale, to 10,000 to 100,000 processors. So we'll look at that. Okay, so what is, I'm going to be real basic here for the first day, and I hope you don't mind. It may insult some people, but I'm going to just do the basics here to get started. And so I just want to take definitions. So what is parallel computing? Well, as maybe all of you know, the hardest part in parallel computing is to get 2 processors to solve a problem together and have it run faster than it did on 1 processor. Many of you had the experience that you run it on 2 processors and it runs slower than it did on 1 processor. That happens to everybody. So that's the beginning and the rigorous definition, but the practical objective today is to scale up to 1,000 processors or more, and that's really hard, and I'll talk in detail about the reasons why that's hard today, and we'll look at that in some particular applications later in the week. What are the issues? Well, you have to synchronize things, and there are different ways to do that depending on different languages. And different architectures support different language systems. And finally, you got to parallelize the algorithm. In some cases, it's not obvious how to parallelize algorithms. And I want to talk at the end about an algorithm which really seems essentially sequential when you look at it. And we'll see that, well, maybe there's a way around that. Performance is the most important thing in scientific computing. And so performance analysis allows you to achieve the performance that you have to have. And I'll talk a little bit about that, not as much as I would like for lack of time. Okay, so what we need really is some key to the secrets of parallel computing. And I've indicated a figure here that's really important. This depicts a critical section. And it's something I tried to draw when I was teaching parallel computing for years, and I could never quite do it. I just couldn't get the figure drawn. And then we're traveling one day near the Grand Canyon, and we saw that. Oh, yeah, it happens to be the cover of a book as well. Here's the book. And of course, this is the shameless advertising section of the talk. So this is all about getting you to buy this book. But I do really recommend it, and most of the lectures are going to be taken from here, and of course the first chapter is available. And I really like this picture in part because my wife took the picture. She risked her life leaning out on the other side of the river to take this. Just so you know, so critical section, what you imagine is you have this challenge to build a railroad around here, but you only got room for a single line of track, or there are environmental issues or whatever. So you're going to have a single line of track, and you've got to manage it. And of course, semaphores were developed by the railroad industry to deal with the single line of track issue so you wouldn't have collisions. Because you imagine you get up going to speed and you make this turn and you hit another train, it could be ugly. So you put some flags up here, that's what a semaphore is, and that's a key technique for synchronization. Well, the book has a lot more things like that in it. And this is one of the key pictures from the book. There are really 3 core issues you have to understand in order to do parallel computing, no matter what application you're interested in. You need to, the center of it is always algorithms, and we'll end up talking mostly about algorithms. You need to understand computer architecture, and I'll say a little bit about that, and I think other people are going to say a lot more about it, especially about GPU architecture is my expectation. And finally, languages are very important. But languages we'll talk about more in the drinking sessions, because there are a lot of war stories here. We never seem to have gotten off of ground zero. MPI is still the technique used mostly, or CUDA if you're programming a GPU. And so these are really what the more or less what the manufacturer gives you, and that's a very low level. And there are efforts higher level, and the book talks about many different languages because, in a way, that's a bottleneck. Everything has got to go through some programming language, and that's a crucial point, but we haven't ever centralized on high-level programming language. There are many attempts to do that, and there are ongoing attempts, and I'll be happy to talk about that, but that's the religion part of the subject, so I'm not going to talk about that much here. So here's the plan for the course. So first of all, I'm going to talk about some really basic notions, influence of memory and load balancing on performance measures, speed up, efficiency, Amdahl's law, and scalability, computer architecture notation, and this will give us a way to see visually the influence of memory on performance. Then I'll switch over to dependence analysis, to look at loop carried dependencies and how one can deal with that. This is something that's critical. It often ends an argument about whether or not you can parallelize a loop. Then we'll look at some basic algorithms. And I'll start with linear systems, where, again, things have been in good shape for a very long time. But I'll then look at scalable algorithms for sparse triangular systems, which is actually sequentially it's the trivial case, but parallel it's the hardest case to do. And we'll look at a couple of different algorithms for that. So that'll get a little bit technical, but I love it. Lots of notation. And then here comes hopefully the new part at the end. Want to look at solving an ordinary differential equation, which you just think of as a sequential process. So how could you do that? If it's a nonlinear ODE, how could you parallelize that? Well, there's a way to parallelize in time, and I want to tell you about that. Okay, so that's the plan for the course. So let's get into it here. So performance. Well, I claim that in scientific computing, performance is a constraint, not an objective. To take the nomenclature from optimization. In optimization, you have the thing that you're trying to get maximized or minimized, but then you have these constraints, which you can't violate. Well, I claim performance is a constraint. You have to have the highest performance that can be gotten from a computer, or nobody's going to use your code. They're going to use the other code that has higher performance. So that's the most important thing here. So I won't dwell much about performance, but just to say that in this book we proposed this standard name for performance. You need a unit of performance, so we proposed a Cray as 1 billion floating point operations per second. I'm not going to insist on this notation, but I just throw it out there to see if it might catch on, to commemorate Seymour Cray, who died way too early, and it really is, in a sense, the father of supercomputing, and did the right thing. He founded his company in his boyhood home, and also the home of a very good beer company. Okay, so let's talk about memory effects. So memory is really the most important thing now in high-performance computing. And the thing to look at is the work-to-memory ratio. So you want to take the number of floating point operations that are being done, or some other metric of work being done, and divide it by the number of memory locations that have to be referenced in the computation. And just to get us going here, let's take a trivial problem. You're going to sum up a bunch of numbers. Always a good place to start, though, because it's kind of a core computational problem. And we ask, how many floating point operations is there per memory reference? We have to reference all these locations, and so the memory the work-to-memory ratio is about 1. And we'll see that that's not good. This is a real constraint. This means that to do one floating point operation, you have to move to memory, and that's expensive with today's hardware. Yes?
So could you hop back?
Yes.
I've seen algorithmic intensity, work memory ratio, the keys unit. Is there a standard definition? Is this what you use in the book?
Yeah, this is what we used in the book. So, in fact, there's a lot of notation here that's changed since we wrote the book and has become standardized. And it would be nice to have it all, it's a new field, so it's yet to be standardized. But yeah, and the way we define it is somewhat non-standard. Is way.
That's a troublemaker. Of course, it has no memory references because all you have to do is compute 3, 5, 7, 9, and so on, and do the arithmetic.
Ah, this is true. This is true. But yeah, that's right. So that would be, but of course that would involve a lot of divides, and you could argue these could be numbers that have been that were difficult to compute.
It is to define the problem, right?
It absolutely is. Yes, and of course the thing I'll tell you about next time. I'm going to give a step back and give a little perspective on computational modeling, which is really what we're all about here. Getting an answer as opposed to computing. Today, and for a lot of the time, I'm going to take sort of a point of view of we've been presented a computational problem. We're just trying to deal with that. And of course, here I'm making some assumptions about how this problem would be approached. But there are many different approaches you could take. But the key issue is that if you have a lot of memory traffic. To do your computation, you're going to be in trouble because there's going to be a cost of moving stuff here. And the thing is that this is getting faster than this is getting faster. And so we're going to have to pay attention to that. So this is a very simple model of a computer, but it allows you to prove a theorem which says that whatever your work-to-memory ratio is, then the maximum performance you can get is going to be a multiple of that, and so you can't exceed whatever the memory provides. So it gives you an upper bound on the number of operations per unit time that can actually be performed, and often that's much lower than the CPU would support. And actually, that's been something that's been known for many years, and say the last decade or so, we've been plagued by the fact that we've had these commodity processors supporting parallel computing, and they have very bad architecture in this sense. And so getting parallel performance was not the hard part. Getting scalar performance out of each individual node is what was hard. I'm not really going to talk about that, although much of what I'm talking about is applicable to that. Now, you could say, well, but I've got a more complicated architecture. I've got a local cache here. And so, yes, that's true, that the more you can get cache reuse, the better things are, and you can do a model for that, and so you can get a fairly precise idea about what sort of performance is available. Here is kind of the big picture. So, there's a difference in performance. So if you can work with things in registers, you get a very high performance. As you move out to cache, the performance will go down. If your problem fits in memory, you're at this level. If you have to go out to disk, it slows down. And eventually, it just doesn't fit in the computer, and the performance goes to minus infinity. So let's get back to the simple sum, and just for sake of argument, talk about an algorithm for solving it. We can just divide up the sum into partial sums like this, and then say each processor could do this partial sum, and then that part is trivially parallel, and then somehow we've got to put it together. So that's a simple model of computation. We have a trivially parallel part that's computationally intensive, and then we've got a communication intensive part to put the sums together. So we'll take that as a simple model. And here is a pictorial way of thinking about it. We've got listed here the indices for the data AI, which we think of as coming from memory somewhere. And we call that an iteration space. That's the iteration space. And what we did was we cut it up into blocks like this and allocated it to different processors, and each processor did the partial sums. And this is called a decomposition, and the size of the decomposition is called the granularity. And that's often called data parallelism. Now, one thing that causes codes not to function very well is a lack of load balance. So let's just define load balance here. So I'm going to take the following definition. So let's suppose that we have a bunch of processes that execute in a time Ti, collaborating on some total job. And I'm going to take the ratio of the average time to the maximum time. And that's what I define to be the load balance parameter. So if that parameter is 1, the average is equal to the max. It means all the TIs are the same. And so that's a load balance problem. If beta goes to, this is always between 0 and 1. And if beta goes to 0, then the load balance is bad. So 1 minus beta is the difference between the maximum and the average. So that's easy to understand that, how that is, the worst case is comparing with the average case. And we'll come back to this, why this average is the right thing in a couple of examples. Let me just go on to that one example here. So what I want to say is the optimal runtime can often be achieved when one processor does nothing. And the take-home message I want to say is that it's not the minimum time that matters, it's the average time that matters. If you said, well, I'd like to define my load balancing by taking the ratio of the minimum to the maximum time, that can be often overly pessimistic. You really want a metric that, it's a metric. If you drive that, in that metric your load balance is 1, you're fine. But it can be that number could be very small. It could be 0, and things are still okay. So I want to claim the optimal time can be achieved when one processor does nothing, and we'll sum n numbers, our just simple summation problem, and I'll choose n to be the number of processors minus 1 times some number k, which we'll choose, plus 1. Okay, so what that means is one algorithm would be to have all but one processor do k minus 1 floating point operations with k summands. So p minus 1 processors have k pieces of data and they do k minus 1 summands, and then there's one more piece of data. And so the last processor only has one piece of data, no summation to do, and I claim that can be optimal. Okay, so I claim when k is less than or equal to p, the fastest possible execution time involves at least one processor doing k minus 1 floating point operations. Since here, all but one processor does k minus 1 floating point operations, I'm saying under this restriction, at least one processor will do that many, and so the algorithm in red is optimal. And in this case, one processor does nothing. So that's supporting my first assumption. So the proof is very simple. You just look at the situation. You just think about how the summands have been assigned. So if all the processors had less than k minus 1, then at most that many summands would have been assigned. And that the total number of unassigned summands would be the total number minus that number that's assigned. And so there would be at least this many unassigned. And if k is less than or equal to p, this is a positive number, and that would mean that we wouldn't have assigned all the summands, and so that wouldn't be a valid algorithm. Okay, so you could have the minimum time be 0, and you'd still have a load balance problem. Okay, so let's just give a quick summary of what are going to be the limits to parallel performance. Well, the key points here are that synchronization matters. If we have processes that are not synchronized, even though their individual times are quite small, they can be out of sync, and the total execution time is large. The load balance has to be near 1, because otherwise you've got some processor that takes too long to execute, and then there are communication costs. So far we haven't looked at communication unless you take the analogy of memory references being analogous to that. Okay, so here's an outline of how we're going to look at limits to parallel performance. The best known caveat is Amdahl's law. Amdahl said basically you can't make a business out of building parallel computers, and so he completely avoided that. It's not clear it's a good business, but nevertheless they are built and used. Speedup is the thing that we're often most interested in. How much faster does the code execute on a parallel computer? Sometimes the issue of efficiency matters because somebody has to pay the bills, and if you're using a machine with very, very small efficiency, you're wasting somebody's money. So we'll talk about these concepts, how they relate to Amdahl's law, which said that you can't get good speed up. And finally, we'll come to the notion of scalability. And this was really a logjam breaking event when this was defined. Okay, so we look back at our summation example. Suppose we were to solve that on a very crude parallel computer, just a network of workstations connected by Ethernet. So in other words, to communicate, we have to just broadcast out over the network. And if we had P computers and we had to communicate P things, it would take order P time to do it. So let's suppose that in our summation problem, the time of computing is n over P because we divided this up into P, let's say, exactly divisible parts. And then to do the communication, we have to have an amount of time proportional to the number of processors. So here's our model of the parallel execution time. So it's n over P plus the constant corresponding to communication, and then of course each processor has got to add the numbers together. In this case, what I'm assuming is that everybody broadcasts their partial sums, and then everybody does redundantly the summation of all the partial sum. Okay, so that's the model, and here's what execution would look like for a synthetic problem where I've just summed up a bunch of numbers with these coefficients chosen. So execution time goes down. Okay, so that looks good. It looks like we're winning, and that's a reasonable thing to do, to present your data that way. But there are more critical measures, and speedup is the first one to look at. Speedup is the ratio of the sequential time to the parallel time. And now you're looking at something a little bit more critical. We're going to now divide this number by the sequential time. So when we do that, when we take our problem, the speed up is the sequential time, which we say is proportional to n, divided by the parallel time. What do we get? Okay, so it's complicated algebra, but this is what we get. We get P divided by a complicated expression. Now, what should speed up be? Speed up should be P. If we're going to have P processors at work, we should get a factor of P benefit, right? I mentioned this early on, this is a long time ago, to a pure mathematician. He said, oh, you're going to get greater than P speed up. And I thought, well, okay, maybe, but not in my lifetime. I don't know where he came. Maybe he was thinking about quantum computing or something else. Anyway, but if you got speed up equal to P, you'd be happy. Now, it actually can happen that you get speed up greater than P. How does that happen? Well, if you remember, we had this picture back here. We said the smaller the problem, the faster it runs. And you do actually see that. So if you had a problem that on one processor is residing out here, and when you use 10 processors, it sits here, and when you use 100 processors, it sits here on each individual processor, you'll get greater than one speed up. And we did see that with some early calculations, and it confused us for a while, and then we figured out what was going on. You don't see it very often. So we'll think of speed up as being ideally like P, and So it would be natural to plot the speed up for a computation against just the number p. So here's the speed up for our little summation problem against number of processors. And now we see something doesn't look so good. Before, it was going down. It was always going down. That was great. You know, we felt we were doing something good. But here, it's tailing off. We're losing here somehow. So the speed up plot is much more demanding. So here's my, advice. If your computations aren't going so well, don't show speed up. Just show the execution time going down and stop when it doesn't go down. Show speed up if it's going well, and then stop where it's not going well. And there's more detail here I'm skipping over. But the most important thing is the efficiency. And efficiency is just the ratio of the speed up to the number of processes. So that's the most demanding thing. So here for that synthetic problem is the efficiency. And now you see something that starts out near 1 and really starts to tail off. And so if you really have a very scalable code, show efficiency. You'll impress the experts. I'll skip over some of these just because they're pretty straightforward. Efficiency can be related to cost, and so you can talk about if you have a particular charging algorithm, how that can be related. Let me go into Amdahl's law quickly. Amdahl said that the sequential fraction of a code would limit the amount of speed up. So let's just jump over to the law itself. He said that the speed up would be bounded by 1 over the sequential fraction plus this factor, which does go to 0 as p goes to infinity, but overall speed up can be no greater than 1 over the sequential fraction. And there he stopped. He said, well, no, it's very hard to write a code without some sequential fraction. And so that limits your speed up. And think about it. I mean, suppose it were 10%. 10% is 90% parallel. That sounds pretty good. 90-10 rule, But that means the maximum speed up would be 10. So he built 6 processor machines, and that's where things stopped. Okay, so, and there's more here I can talk about, but let's just quickly, efficiency can be related to Amdahl's law in an interesting way as well, but let me move on. Yes, go ahead.
One quick, do you have any comments on Gustafson's law?
What's Gustafson's law?
Well, with Amdahl, you have a fixed size problem. With Gustafson's is, when you look at parallel problems or big problems in general, your problem size.
Okay, this is what I call scalability. I think I'm out of touch on the names here. I think Gustafson gets credit.
Fred Gustafson from IBM is what he's talking
But I've never heard
That's new. I've heard someone say.
I need to check my references. We'll get to the scalability. You're talking about scalability, so yes, that's coming. Okay, load balance and efficiency. This is just a return to, remember how I defined the load balance parameters, the average versus the max. Here's a theorem that relates the efficiency is bounded above by this beta parameter. So this is another reason why I like this definition of load balance. It gives you an upper bound on efficiency. So if beta is small, efficiency is going to be small. Remember, the min to the max could be 0, and you still have the optimal program. But with this one, it really gives you a bound on efficiency. And you can talk about putting 2 pieces of computation together, but let's move on to scalability. So there's a bit of history here, but this is NANet in its original incarnation, and an email from Alan Karp, who'd been at the 2nd SIAM conference on parallel processing in Norfolk, those many years ago. Where's the date on this thing? 85, a while ago, 25 years ago. So what he said was, I've heard talk about 1,000 processor systems, 1,000,000 processor systems, but I don't believe anybody can get a speed up of 200. And he put some money on it, and that was great. And everybody got excited about it. Some definition. The email went on, and then there was a lot of chatter following, making this more or less a well-defined problem. And lo and behold, somebody met the challenge and got on 3 different problems, got scalability speedups of over 200, and that morphed into what are now called the Bell Prizes. Gordon Bell put some real money behind it, and now these are awarded at Supercomputing. But the most important contribution of 4 was this notion of scalability, that if you have a large problem, you'll use a large machine. If you have a small problem, use a small machine. Let me just think about time here. Yeah, okay, so let me quickly go through this.
If you go 15 more, I'll just shave off some from mine at the end.
Oh, okay, okay, and then I'll buy the drinks. How does that work?
We are all the same way.
Everybody. So just remember, when you're going in that reception, say moi. Okay. So we take our little problem here. Here's our summation problem. The efficiency worked out to be this funny formula. And so what does this mean? This means that if somehow we contrive to have the number of processors squared equal to the number of things being added, this efficiency would be a constant. So that sounds good. So would be a good solution to that problem. And so what we can do is we can define notions of data-dependent speedup. So we just, for a given n, we record the sequential time, the parallel time. That gives us our data-dependent speedup, and correspondingly the data-dependent efficiency. And the definition they gave of scalable is if there is a minimum efficiency. So it says that for every n, there is a p of n, so a function of n, such that the efficiency is bounded below by epsilon, greater than 0, for n arbitrarily large. This is an interesting definition for a lot of reasons. One of the things is it involves a function here. And it's kind of like an epsilon delta proof. There's not just one function. There are lots of possible functions, so that makes it kind of interesting. If you want, back here, here's our function. We're saying we're going to take p of n to be the square root of n, and that would give a constant there. And but that's not the only thing that we could do. We could do other things. So here's the scalability analysis for summation and some of the examples that you can use. Now, so what happened to Amdahl's law? So here we said we could have arbitrarily large problems. Amdahl said, no, there's a sequential fraction. Okay, but the sequential fraction could go to 0 as a function of the data size. And this is the thing that I think Amdahl wasn't thinking about. But he was thinking about commercial applications, not scientific computing, where you typically have a natural grid size that is n, and you actually can control the sequential fraction. Okay, another important concept is to talk about scalability with respect to memory. So you might have something that scales up, but at a certain point, it doesn't fit in your particular processor. So if in the scalability process, the size goes without bound, then you would say it's not scalable with respect to memory. So that's leads to the notion of memory constrained scaling. So you would say that for the number of processors, for the scalability definition, the amount of memory used is bounded by a constant. And of course, it turns out that the summation problem is not scalable with respect to memory. And so, am I doing this right? Yeah. So I'll let you read over that. Let's go on now to weak scaling. What I've talked about is the classic definition of scalability, and let's just go back to the key ingredients. It really has to do with looking at this quantity, how much speed up you get as a function of n, where you get to pick the p as a function of n. Now, that's great, but if you want to really verify it, n might get really large, and you might not be able to solve that problem on one processor. So this is now called strong scaling. And so strong scaling is good, but it's not something you can often verify. And you may not really care because, again, if you go back to the simple way of talking about scalability, solve a big problem on a big machine and solve, if it's a small problem, use a small machine. in that scenario, you wouldn't ever solve the big problem on one processor. And practically speaking, you may not be able to do that. So that brings us to the notion of weak scaling. So the idea of weak scaling is you can't really compute this number. So maybe you can model it. Maybe you have an algorithm that grows in a particular way with n. And let's take multigrid, where everything is linear in n. So the computation time is a constant times n. And if you had an ideal performance, you would get this sort of performance. And you'd get the sequential time divided by the parallel time. And so that ought to be perfect speed up. And so what you do then is you can define, you say, okay, well, if that were if this were the time on a very large problem, if I could do it on that one processor, then it leads to the following definition of efficiency. So what you do is you take a computation with a doable amount of memory, n, and then on P processors, you have the same amount of memory on each processor. Now, this is specific to a problem that's where the complexity is linear in the computation. Other notions of scaled efficiency or weak scaling would have to be done in a different way. But this is what is appropriate in that case. And so with that notion of efficiency, you can begin to look at things like multigrid. And so that's what's being done here. This is a computation we can now think about in terms of weak scaling. So this is a particular form of multigrid that Dechuan Shi and I have been interested in for many years. It's kind of the dumb approach to a V cycle. So in multigrid, you have these V cycles, W cycles, and so forth. Our approach is just to say, well, it's been well known for many years that the V cycle runs out of parallel work at the bottom of the V, and so we say, well, we'll just stop. We'll just call it a U cycle. We'll stop at some intermediate point. And I forget the notation here. I think J is the level at which we stop. And that's the coarsest mesh that we use. And then on the coarsest mesh, you have to have a solver. And we picked another parallel algorithm, parallel version of SOR that we developed some years ago. And so we use that as the sequential solver on, or the solver on the coarsest mesh. And then these are the computations that we get. These are the performance numbers that we get. So this is pretty good weak scaling, we would argue. Maybe not the best, but this is an example of the use of the notion of weak scalability. Okay, so here are some of the references, and in particular, you said Gustafson, right? So maybe that is the right way to say this. What did I have? So the scalability definition is definitely due to, the reference was here a minute ago. Where did I give my credit? I give the credit here. It eludes me. I was pretty sure it was reference 4. Okay, yeah, 4. So 4 was indeed the, so John Gustafson. Good, so that must be, that's a good name for it. I like that.
It's the right reference, yeah.
I don't know, I'm sorry, I never did try to assess different contributions to that piece of work. It was a landmark piece of work, but I never dissected who did what with it, so I'm not competent to say, but at least we're talking about the right person. And that definitely was a critical step in getting the whole process going. It's interesting, one of the things we cover in the book is standard notions of parallel complexity that the complexity community in computer science has looked at. There's a lot on parallel complexity. But this particular notion of sort of resource constraint, scalability is a resource constrained notion of complexity, was never looked at. And I was sort of shocked by this, and so I asked the computer scientist, the complexity theorist, about this, and I sort of expected him to be ashamed. Here was this very important notion that had been missed by the complexity community, and he said, "Oh, great, a new definition. Let's go off and prove some more theorems." So anyway, but this was a very important development in the subject, and there are more references there for you to look at. So. With that, I'll stop for today and encourage you to come back tomorrow. Not at this time. Somehow I kind of am slow, so I can sleep in the morning. So they gave me a later slot and every time I get a later slot. So it'll be a little bit later tomorrow, but I will look forward to seeing you then. Thanks.